Hello, everyone. Come on in. Looks like we got 19 of you already. Good job. So hopefully everybody's seen their homework now and been to my lab and mastering. Anybody have any questions on anything so far? All right, looks like we're now up to 21 students, which is all the students, so that should be good. Are the notes from class in Canvas? Okay, so someone asked me about this on email. If you look, if you were watching class on the first day, the two things I explained was I put the notes almost immediately after class on Google Docs. So if you look up in Canvas, there's that area where it says important course links and information, or course documents and information, something like that. There's a link to my Canvas, to my Google Docs for this class. So that's where you find my notes. Also, my videos, I post them as soon as I can to my YouTube channel. So you can also go there to get my actual videos. There, I don't put them on actual studio or any of the stuff that we have built in Canvas because it takes too long. So what I have them do is I record them to my local computer. That means I don't I don't have the bandwidth delays that on the video that you'd have otherwise. Because if I record it to Canvas, then the internet's connection would be between the camera and the actual recording, and you'd get that digitized looking picture. So I record it here, and then I have to wait for it to convert, and then I have to upload it to YouTube, which is another long process. So I usually get it by the day after, if not the same day. So you can find, like I said, my lecture on my YouTube channel. That's www.youtube.com/Billy with a capital B, Younger with a capital Y, Physics with a capital P, Solutions with a capital S. The video for the last class should be on there. Let me see. Maybe I didn't make it public. I see in my list, Introduction to the Course, Scientific Process, January 11th, 2022. So yeah, that's the first day's class. It's right there. There's one January 10th as well. Yeah, January 10th, January 11th, and January 12th are all up. So I see 1, 2, 3, 4 videos posted already. So they should be there, and they're all listed as public. I've had 12 people view the January 10th one, which would have been not your class. That was the class before. That's a 242 class. But yeah, your January 11th is there, as well as I think the lab should be up there. But if you look, when you click there, let me share my screen real quick. So I'm looking right here at my course, and if you look at, let's say, this course right here, I'm looking at it a weird way that you won't necessarily see. But the key to figuring out which class it's for is knowing your section number. So your 240 is that this is PHY 241 D01B for 11122. So you know that's the right class.
That's the lab upload, not the lecture.
Is it? Thank you. I was wondering. I forgot after the fact because I had like three videos in the can. I forgot to check which one was lab, which one was lecture, and I sort of just did them in the order I thought it was. So this one was the actual lab, right?
Yes.
Okay, and that means I labeled it incorrectly.
Yeah, and there's no lecture video posted.
I wonder if I posted the other one twice then.
Yeah, there is 2 Physics 2 videos.
Okay, let's check this. So that was, well, this one's 1 minute, 1 hour and 28 minutes. This one's 1 hour and 19. That means they're supposed to be different, but that could be my 242 class.
Yeah, they're both from 242.
Oh, okay, gotcha. Then that means I just recorded the wrong one. I'll put that up. I apologize. Thank you for catching me on that.
Oh yeah, no problem.
All right, so I'll correct that immediately. The good news is we didn't cover that much material. The main thing we covered was the actual syllabus. That's what took the majority of the time. And then we talked about the scientific process, where I sort of notice when you actually do the online homework, conceptual questions and stuff like that, that'll be more in tune with what the book says. What I was giving you is a real life introduction. What come test time, Basically, you'll see the practice tests are made of questions that you've been doing or that you will do on the actual test. So you'll get a better feel for what the right questions are and the right interpretations are. My way isn't what Giancoli says. So just keep that in mind. He's slowly progressing to get to the more modern version of theory versus hypothesis, but he's not a skeptic like me, so he's not quite in that realm of places where we have to correct things. I follow the Skeptic's Guide to the Universe and James Randi and people like that, Skeptic Magazine, where we spend a lot of our time debunking myths. And one of the pet peeves of the world is really people misusing the word theory. And if you're more in the academic realm as opposed to the skeptic realm, then you're more likely to not care about it. So that might be why you might run into a different interpretation of the science. Of course, you are supposed to know scientific notation. Anybody in here need a refresher on scientific notation? You can chat directly to me and then no one will see it. Otherwise, I'm just going to keep moving because most people know that because they've had it either in high school or in chemistry in high school or chemistry in college or whatever. So January 11th, I want to make a note of that. You said that's for lab. So I did make the January 11th lab video. That's a check, but January 11th class. And that's 241. Okay, thank you. So I recorded that, so I'll know to do it right after. Actually, I can probably do it at 12:30. So my last class today until I start my lab is over at 12:20. That usually gives me a little bit more than an hour before my lab. And that's enough time, given the bandwidth that I have, to upload the video. So I got to just find it right after my 11 o'clock class, find it, and then start uploading it. So it should be up there by 1:30 today. So error propagation refresher would be cool. Yeah, so yeah, there is actually an online version of that. Let me share my screen again too. Error propagation is something we're going to continue to beat up the whole year or the whole semester. And then if you take 242, you'll see it again there. If you do search across my channel, just look for a word error. A more concise introduction to error analysis. That's what we're looking for here. So this October 1 video is where you can find the same version of that. But the main thing that you're supposed to learn, of course, from it is that sig figs actually make a lot of mistakes. They sometimes overassume what you know, sometimes they underassume what you know, and they just get it wrong. And so they're not really a robust scientific way of doing it. What you're supposed to do is take many trials of every measurement you do, and then your best estimate of what that trial or what that measurement is your mean, your average, basically. If the several trials had differing levels of error, then you should do a weighted average instead of just an average. And that's just your best estimate. So that's the number before the plus or minus. Then you're supposed to calculate the standard deviation of those measurements, and then the standard error of those measurements is gotten by taking the standard deviation divided by the square root of the number of trials. And that's the number that goes after the plus or minus. So when you go to make a measurement as a lab, you would report the measurement as the best estimate plus or minus the standard error. So those are the big concepts that you're supposed to get. Then when you use such measurements to calculate something like a formula, like for volume equals length times width times height, to find what comes after the plus or minus, you have to do the error propagation formulas. So anyway, everybody sees that. Hopefully a better concise intro to error analysis on October 1 and a concise intro to error analysis. Those two videos are basically that more or less that same lecture I gave you in lab the other day. I want to stop sharing and remind what we learned. So I just said it in word form, but I want to write that down. So any measurement X should have a value X bar. You probably don't want to look at my head, right? Who wants to look at my bald head? My bald liver spotted head. So anyways, yeah, it's supposed to be your best estimate plus or minus sigma x, and x bar is generally understood to be that, or sometimes they'll use x in brackets like that. And that needs to be focused a little better than that. Come on now. There you go. Which is really x1 plus x2 plus ... on up to plus xn divided by n. Okay. That's assuming each measurement has the same amount of error. If each measurement has a significantly different error, then you really need to take a weighted average, but we're not going to do that at all this semester, so you need not. Okay. Sigma x, on the other hand, there's this, which is called the standard deviation. Okay. And that's the square root of x minus x bar. Let's say x1 minus x bar squared plus x2 minus x bar squared plus ... plus xn minus x bar squared, square root of all that junk, divided by n minus 1. And then sigma x is just s sub x over the square root of n. So that's the number that goes over there. And then you have, in general, the uncertainty in f of x, y, z is equal to the square root of the sum of the squares, partial of f with respect to x squared sigma x squared plus partial f with respect to y squared partial y squared plus partial f with respect to z sigma z squared. Okay, so that's how your error propagates when you use a formula f of x, y, z. So you had like an x that would be like this, that has some best value and an error. And you take the derivative of this function, pretending like the y and the z are constants. And that derivative is called the partial derivative. You square it, multiply it by this part right here squared. And then you take the derivative of this acting like the y, the x and the z are constant, you square it, and then you take the sigma y and square it. And then you add to that, again, take the derivative, this time acting like the x and y are constant, square that, and then multiply it by the square of the uncertainty in z. Take the square root of all that, and that spits out what would be after the plus or minus in f. So then your f would be f of x bar, y bar, z bar, plus or minus sigma f. Okay, so that's the big rules. Those are the big things you need to know. Those are the things you need to be able to calculate. The good news is there's a lot of simplifications for this. Like I gave you at the end, if f of x, y is just a product of x's, y's, z's, and so on, then it's just going to be the fractional error of f squared plus a fractional error of f squared with respect to, or excuse me, the fractional error of x squared, fractional error of y squared, fractional error of z squared. And if you had more factors like w, u, so on and so forth, it just continue to be the sum of those squares. So f of x, y, z equals x plus or minus y just gives me but f of x, y, z equals x times y times z gives me that the uncertainty, the fractional uncertainty of f is equal to the fractional uncertainty of x squared plus the fractional uncertainty of y squared plus the fractional uncertainty of z squared. And the formula that we're using here is the fractional uncertainty of x is just the uncertainty in x. So that'd be that little number right there divided by that number right there. Okay.
Do you have a way to maybe focus the webcam a little bit more? It's a little bit too blurry for me to decipher.
Yeah, I think the blurriness might be the internet. So I will bring it closer, but I'm not sure it's going to help. There you go. So let me start off with everything we had here. So every number that you work out in a lab, or every measurement you take in a lab, should be expressed as some number, which is the best estimate, X bar, plus or minus its uncertainty. The X bar generally is the average that you see up there, X1 plus X2 plus ... divided by N. The sigma X is actually the standard error, which you see right there, but that comes after you find the standard deviation, which is taking the sum of the squares of the deviations, dividing it by N minus 1 and taking the square root of that. Once you have that standard deviation, you just divide it by the square root of the number of trials and you get the standard error, which is what goes right there. If you then take measured quantities within a lab like X, Y, and Z, and you have to use those to calculate some other quantity using a formula F of X, Y, Z, then this is how you find that uncertainty in the F, given the uncertainties in the X, the Y, and the Z. So you take the derivative of F with respect to X, pretending like the Y and Z are constant, you square it, multiply it by the uncertainty in the X squared, you add that to the derivative of F with respect to Y as if the X and Z are constant, you square that, multiply it by the uncertainty in Y squared, and then you add to those two terms the derivative of F with respect to Z, acting as if X and Y are constants. You square it, multiply it by the square of the uncertainty in Z, take the square root of all that, and that's what goes in the plus, after the plus or minus of your function. How you actually calculate your function is you just use your function, like if your function is X, Y, Z, X times Y times Z, then you're just going to do X bar times Y bar times Z bar. That's your best estimate of F, and then plus or minus that sigma X gotten by that formula. The good news is if it's all addition and subtraction, you're just going to get a quadrature relationship where the uncertainty in F is just the sum of the squares of the uncertainty in X, Y, Z, W, X, whatever. As long as they're all added together or subtracted from each other, anything like that, and they don't have twos in front of them or threes or anything like that, the coefficients are all one, then that formula right there works. Also, if they're all a product, X times Y times Z times W, then their fractional error, which is just the error divided by the best estimate, their fractional error is squared, add up, and then take the square root of that, and that gives you the fractional error of the function. To get the sigma F, now you just multiply it by your best estimate, and that'll come back to be just sigma F. That happens to work also with X over Y, or Y over X, or XY over Z, or Z over XY. All these formulas work this way when it's just pure multiplication and division. So that can avoid a lot of derivatives, but that's the main rules that we're learning. Hopefully that was in close enough for everybody to see, or just grab a screenshot or whatever. I've now focused it back to this other part. Did that help? Whoever that was that asked me, was that Ailey or Emilio or?
Yeah, thank you.
No problem. Oh, it's Julia. Thank you. So yeah, and I apologize about not having that video up. I was so excited that I got them all done. I must have just did a bunch of the same stuff over and over. All right. So now that's basically a recap of all the stuff we covered actually in lab. It was my understanding that we ended up having all of my students are in my lab. Is anyone in here not in my lab? Please chat if you are. I'm just curious, make sure I didn't miss anybody. It looks like I'm right about that. Okay, so what we have left now is I want to show you how to convert units, which probably most of you know, but maybe not. So the big thing is I'm going to show you a precise way of doing it that always works. So this is converting units. Now, when I say converting units in this case, now that looks really bad, like a kindergartner wrote it, but anyways, I don't care. So converting units, basically, there's a couple of ways you can do it. There's some that are logarithmic. There's some that are additive. There's some that are linearly related. These are all multiplicative. The other ones, logarithmic, is like decibels. The ones that are linear are like Celsius to Fahrenheit. I don't know why I put it, see over there, are Fahrenheit to Celsius. And additive are like Celsius to Kelvin or Kelvin to Celsius. Okay, so those are the ones I'm ignoring right now by doing this. All the other ones we just do by multiplication. So for instance, if you had 3.80 miles, and I'd like to convert that to meters, then I could do that very easily. But the trick is to convert multiplicative units, you can only multiply by 1. Okay, but 1 can be written a lot of different ways. 1 can be this, 1 can be this. What can be 2 over 2, or even pi over pi. Or here's where it starts to get a little more abstract. It can be 1 foot over 12 inches. Or it can be 128 ounces over 1 gallon. Or it can be 1 gallon over 128 ounces. Okay, notice how you can flip them over. The main thing is we're going to treat it like an algebra problem where the units are like an x. So this is 3.80x. So if you have an x in the numerator multiplied by a fraction that has x in the denominator, the x's will cancel out. So I'm going to use, this is kind of odd, you can actually look in the front cover of your book and you'll find a conversion straight from miles to meters. I'm not going to use that. Okay, I'm going to use all the values that I truly know. I'm just going to write this as miles, and then I'm going to say, all right, I'm going to multiply this, and I want to get rid of miles. So in order to get rid of miles, I need the miles to be on the bottom. I happen to know that 1 mile is equal to 5,280 feet. Now, this might seem weird, but in fact, I know the string of conversions that get me from feet to meters. So I'm using that because I know them off the top of my head and they're exact. So if this number has 3 sig figs, the answer has 3 sig figs. If this number had 4,000 sig figs, the answer will have 4,000. So now I've gotten rid of the miles and I want to keep going. So I also happen to know that 1 foot is equal to 12 inches. So this foot cancels out with that foot. Now I'm up to inches. Now I also know that the exact conversion between inches and centimeters is that 1 inch is equal to 2.54 centimeters. That's exact. That's what makes all this conversion so perfect. Notice how I'm using a different slashing symbol to cancel out each one. That's really nice because it can let you see if you look back and find any errors you might have made. So I've now gotten to the metric system. I'm now in centimeters, but I also happen to know that there are 100 cents in a dollar, and therefore there's 100 centimeters in a meter. So I'll say 100 centimeters is equal to 1 meter. And what I'm going to do is I'm going to do a curvy slash like this from bottom left to top right. Now I've actually used a different slash symbol for each of them. And all I have to do is do the computation. Now, the way you can do this that always works and keeps you from making a mistake is you can multiply all the numerators and get a numerator, then multiply all the denominators, which I can just add now and say, okay, this denominator is obviously just going to be, well, it's would if the pen would write. Okay, so there's the denominator, and then I'll make a new denominator over here. So what I'm going to do is I'm going to multiply 3.8 times 5280 times times 12 times 2.54. And I know what you get when you multiply by 1, so I don't need to do that. You can see on my calculator that I did 3.8 times 5280 times 12 times 2.54. So this is 611.5507. And that's meters, because that's the only unit that exists still. Notice everything else has been canceled out. Now I do 1 times 1 times 1 times 1 times 100. So if I actually multiplied that, you would see it there, but why bother? 1 times 1 times 1 is just 1. So then I multiply it by 100. So in fact, what I see is this is 6,000 or 61,150. So my decimal was here 12.07 meters. 1, 2, oh, excuse me, went the wrong way. 1 meter, 1 centimeter, 100 centimeters equals 1 meter. Yeah, that's right. Sorry, I moved my decimal to the wrong direction because I might be drunk. That might be the problem. Maybe I'm drunk. I'm not sure. So yeah, and this answer can't be right because it's 3.80 that there you go. Did everybody see the mistake I made? I read my calculator and it says 611.5507. It said an E3 there. I missed that. So it should have said this times 10 to the 3. My fault. So watch out with your calculator. Whenever that little E comes up, that means it's not an error. That means it's times 10 to the whatever power. So that was me just being a goober. I can now move the decimal 2 places to the left, and I'll see that it's 6.11557 times 10 to the 3rd meters. Now in physics, in science in general, in nature in general, numbers are meaningless unless you know the unit that they have or that they have no unit at all. So you always got to make sure you do that. Put the unit on the end. In this case, obviously I only had 3 sig figs, so I really should call this 6.12 just to proper round it. Okay, so I'd say 3.80 miles is about 6.12 times 10 to the 3rd meters. All these digits beyond here, I mean, even this digit right here is doubtful because when you make a measurement, that last digit is doubtful. So that means this digit, the 1, is doubtful. We rounded it to 2 because this number is bigger, is 5 or larger. Some areas in science ask you to, if it's a 5, you say, is the next number odd or even? If it's odd, you round it up. If it's even, you round it down. Some of it say, I suspect some of them say actually exactly the opposite. That can remedy by the problem of overcounting the 5 as a increase. And then all the numbers 6, 7, 8, 9 cause you to round up, and all the numbers 1, 2, 3, 4 cause you to round down, which would be just truncate. So that can be done too, but I'm not going to require any of that fancy stuff in my lectures or my lab. Okay, you just round. So you got 6,000. So did you notice a times 10 to the 3rd? Because that might have been the problem. Your calculator might also have been on scientific notation, or excuse me, engineering notation or something like that. I suspect this answer is right. Let me do it again. Anybody else back up my calculation or get the same result that I did? So we can have a disinterested third party confirm which answer is right. Right now I'm looking at it being this. And when I did it on my calculator, you can see I did 3.8 times, well, maybe you can't. Now you can. 3.8 times 5,280 times 12 times 2.54. I don't really have to do the 1. And that gave me, according to my calculator, that gave me 611.5507 times 10 to the third. And all I have to do divided by 10 is move the decimal 2. Actually, did I do that wrong again? Yeah. So this is right. I moved my decimal 2 places to the left. That's what happens when you divide by 100. And that made it 6.115507 times 10 to the third. So this should be correct. You can give it another try. Did you get the same answer I got this time?
They're both the same answer. He just used the version without scientific notation.
Okay, gotcha. Good deal. Oh yeah, he did, because he would have had the decimal right after that. Gotcha. Thanks. Nice catch there. All right. So yeah, that's the way you convert units, but it can get more complicated than that. One of the best things I like to do is my mom used to tell me my mouth was running a mile a minute. So you say 1 mile, 1 minute, and you go through and let's convert that to miles per hour just out of curiosity. So I'll say that 1 mile is equal to 5,200. Oh no, I still want miles, so I'll leave that. I'm going to convert to miles per hour, and it's already got a miles in it, so I don't need to do that. So really what I need to do is convert the minutes to hours. So what I'm going to do is I'll say there's 3,600 minutes, or excuse me, 3,600. No, it's 60 minutes. I was thinking I was going to seconds. There's 60 minutes in 1 hour. So that one's really super easy. You can see the minute crosses out with the minute, and I get 60 miles per hour, which I always think is just a funny thing to tell students. And you'd think, since I think it's a funny thing to tell students, I wouldn't make mistakes and try to put the constants down there, but you would be wrong, because Mr. Younger's obviously a heavy drinker or something. Again, not really. I'm just making jokes here. All right, so that's another one you can do. Notice this time it was a conversion of something in the bottom. So to get rid of that thing in the bottom, I had to introduce that same thing in the top. That's why the minutes canceled out with the minutes up here. So that's a illustrative point about units. Now you might also have something neat, like one of the coolest things I know is the fact that water has a mass of 1,000 kilograms if you're measuring a cubic meter of it. So 1 cubic meter of water, which is about 39 inches by 39 inches by 39 inches. A meter is about the height of the top of a doorknob. Okay, so if you go from the ground to the top of a doorknob, that's about a meter. So imagine a cubical box that's 1 meter by 1 meter by 1 meter. And you can see that's a pretty big thing. It's sort of like those water containers you might have seen down along Pungo Road or Fentress Road. You'll see them on the side of some farms. It's a big plastic, sort of white clearish plastic thing in a steel box. Basically, those are very near a cubic meter of water. And in fact, since a kilogram is 2.2 pounds, that would be 2,200 pounds. That's what we call a large ton, or you might say a short ton is what you call 2,000 pounds. So let's look at the conversions that can go from here. So for instance, what we can do is we can convert to grams per cubic centimeter. So if I want to convert from grams per cubic centimeter, I can say, well, I know that 1 kilogram is equal to 1,000 grams. And then here's the tricky part. Not only do I have something in the bottom that I got to convert, it's to the third power, which means I have to do the factor 3 times. So I'm going to say I want it in centimeters, and I'll know that 1 meter is equal to 100 centimeters. That gets rid of one of them. Now I do another meter, 100 centimeters. That gets rid of 2 of them. Now I do it again, 1 meter, 100 centimeters. Now I've gotten all 3 of these marked with that, and I've gotten this kilogram marked with that, and you can see the result is grams per centimeter times centimeter times centimeter. That's centimeter cubed. And you can see basically what you did is you multiplied 1,000 by 1,000, got 1,000,000. And then you divided by 100 times 100 times 100, which is 1,000,000. So you got 1,000,000, or excuse me, kilograms divided by 1,000,000. And actually that wasn't kilograms anymore. That was 1,000,000 grams divided by 1,000,000 cubic centimeters, which equals 1.000, because I'm assuming these are 3 sig figs, even though that's not consistent with my rule that I'm using in lab, grams per cubic centimeter. So that's the density of water. And that's actually fresh water at like 20 degrees Celsius, I think. So that's a common number. It's one that you should probably commit to memory. But you can do other neat things about it. For instance, the concept of a liter, 1 liter, which is abbreviated 1, normally we use capital L. That's actually defined to be the volume of a box. That's 10 centimeters by 10 centimeters. I'm trying to make sure y'all can see that that's an M. I tend to shrink out on my M's there. And then 10 centimeters again. That is what a liter is. So if you use the formula for volume, you see that's equal to 1,000 cubic centimeters. Everybody see that? Okay, so because of that, 1 milliliter, which equals 1/1000th of a liter, that's what milli means, is equal to 1/1000th of 1,000 cubic centimeters. And now you see this cancels out with that, and you get 1 cubic centimeter. So 1 milliliter is equal to 1 cc. That's another way of expressing it. Okay. This will inevitably happen as you grow older, or those of you that are already of age to have had a child. When you have a baby, your doctor will write a prescription for a certain number of cc's every 6 hours. And then your pharmacist will give you a bottle that says a certain number of milliliters every 6 hours. And you'll be like, wait, this is milliliters. The other one's in cc's. Is he poisoning my child? No, it just happens that the milliliter and the cc are equal. Any questions on that? Okay. Well, a neat thing you can do is you can also do water and see that 1.000 grams per cubic centimeter. By the way, if you wanted to make this salt water, they usually just put a 2.5 or a 2.9 right there. So 1,029 kilograms per cubic meter is like ocean salt water, or 1.029 grams per cubic centimeter is ocean/salt water. That's a rough estimate we use in problems. But in this case, I'm going to convert it to ounces per fluid ounce, because that's a weird little unit, right? Ounces per fluid ounce. People don't even realize sometimes that there's actually 2 types of ounces. There's the ounce, that's a unit of weight, which is 1/16th of a pound. And then there's the ounce, the fluid ounce that's on your bottle of water, for instance. And that's supposed to be 1/16th, at least in America, that's supposed to be 1/16th of a pint. In Great Britain, it's 1/20th of a pint. So they differ between the UK and the US versions of fluid ounces. But let's see what this turns out to be. Well, if I want to convert grams per cubic centimeters to ounce per fluid ounce, then what I have to do is convert from grams and try to get from grams to regular ounces. What I happen to know is that 1 ounce is equal to 28.35 roughly. So 1 ounce is equal to approximately 28.35 grams. So this is approximately, it actually, I know it up to 4 decimal places. So we were only given 4, and I actually know it 2 digits beyond this. So this is 4 digits. So that's good enough. okay, to maintain our 4 digits. So now I've gotten rid of grams, and now cubic centimeter. What I know as a cubic centimeter and how that relates to a fluid ounce is this. I can say that 1 fluid ounce is equal to 29.57 cubic centimeters. So now this cubic centimeter is canceling with that cubic centimeter. And you see these two numbers are so close to each other that you find it's still very, very close to 1, even in this whack job unit. So 29.57 divided by 28.35 is equal to 1.043 ounces per fluid ounce. Okay. So I think that's a pretty exhaustive set of examples on unit conversion. Is there any part of that anybody doesn't understand? Okay. Another thing that is sort of big in this chapter is we want you to be able to do what we call Fermi calculations. So Enrico Fermi was a Nobel laureate. I think I mentioned him. I might have mentioned him in your class. I can't remember if I mentioned him in 242 or 241, but he's basically the guy that gave us the first sustained nuclear reaction. In other words, created our first nuclear power plant, and he did so at the University of Chicago. I think it was under their football field. And he also was one of the major scientists that helped steer our Manhattan Project to be able to work out the technicalities of creating a nuclear weapon, specifically the atom bomb. And then later, another guy comes along and helps us get the hydrogen bomb, which is quite different. But Enrico Fermi was really big behind all that. And he came from an era when if you were a scientist, you were a scientist. You know, people that did good science, Einstein, Enrico Fermi, they were good experimentalists as well as a good theorists. And Enrico was probably the best of both, at least at that time. So Enrico Fermi was really famous for being able to just quickly quantify any quantity. Like, for instance, at the first day we dropped, it's called Trinity, the first nuclear weapon we dropped that actually worked. We never failed, by the way. We didn't drop any that failed, but the first one we dropped out in the desert in New Mexico, and he was about a kilometer or a mile away roughly. And when it exploded, he could see the pressure wave coming towards him. He picked up some blades of grass, tossed it up in the air, and then watched it move. And then off the top of his head told him exactly what the kiloton rating was on the explosion. Later, with their instruments, they calculated and found that he was within a few percent of being exactly right. And the reason he did it was because he's brilliant at making approximations. And we like to be able to do that as what we call a back of the envelope calculation. So for instance, you might wonder, how thick is a sheet of paper? So I will take and I look at, for instance, my book, Giancoli, Physics for Scientists and Engineers with Modern Physics, 4th edition. That looks like it's a good 4 centimeters thick to me. And in fact, I know the book has, let's see how many pages it actually has. It looks like after we stop numbering pages, it has at least 76 beyond that. So I'm going to say the last page is page 1228 plus 76. That'd be 1298. That'd be 1304. So I'm going to say the book has 1,304 pages and is about 4.0 centimeters thick. I estimate that to 1 decimal place. So I might say that the thickness of a page So if you took one page and you stacked it on top of another, then you get 2 pages thick. If you stacked another, you get 3, stacked another, you get 4, 5, 6, keep on doing that till you have 1,304 pages. What you've basically done is added repeatedly the same quantity. Whenever you repeatedly add the same quantity, that's equivalent to multiplication. So that tells us to get the thickness of the page, we want to do the opposite, which is to divide. So I'm going to state 4.0 centimeters and divide it by 1,304 pages. And that'll give us the centimeters thickness per page. So if I take 1,304 and I divide that by 4, excuse me, I'd take 4 and divide it by 1,304. I don't know why I said that backwards. And I get 3.1 times 10, there's where I had an E again, times 10 to the negative third centimeters. So even on the centimeter scale, centimeters of thickness. So centimeters of thickness, that'd be 0.0031 centimeters. If I actually wanted to make that millimeters, I could move the decimal 3 places to the right, or excuse me, 1 place to the right, and that would say 0.031 millimeters. If I wanted to make it microns, I could move it 3 places to the right there, and that would be 31 micrometers. Okay. And it turns out that is a very good estimate of the thickness of a page of paper. So you can, of course, now compare your results to see how good they are. This is a wonderful thing to be able to do. Just quickly get a rough estimate of what some numerical value is that you need. Like one of the ones your book talks about is Enrico Fermi quickly calculated how many piano tuners there were in San Francisco. So that's like a crazy thing, but it turns out to be about right. His result turns out to be right. You can also look at example 1.6. They actually said the thickness of a page. Oh, actually, they did the same example in our textbook. Sorry about that. And then they measured it with a micrometer. So you see, that's a pretty good thing to do. Another one is, how many fruit flies or how many house flies can you fit in your room? So you look at the room that you're in, maybe it's your bedroom, maybe it's the living room or whatever, and you estimate the length times the width times the height. You say maybe the height's 3 meters. If you got 9-foot ceilings, that's a pretty good estimate. Maybe the width is 24 feet. So that's about that's about 8 meters. And maybe the depth is maybe 15 feet. So that would be maybe 5 meters. So 3 times 5, or excuse me, 8 times 5 times 3 would be the volume. So volume would be 8 meters times 5 meters times 3 meters. And of course, you get 120 meters there. And you say that, and that's meters cubed, by the way. And you say that's the volume of your room. One of the things I might ask you then is how many houseflies can fit in there? Again, this is something where it requires you to make understandings of how big these units are. So the meter, like I told you, is about the height of a doorknob. You might look as your fingernail, your index fingernail is about 1 centimeter wide. That's a pretty good estimate. You could also see right there, there's a 3 to 4 centimeters. My finger's a little bit wider than a whole centimeter, but that gives you an idea of roughly how big it is. Millimeter, which is these little marks right here, they're about the thickness of a fungus nail. So my nail's normal, so it's too thin. But if someone had one of those thick, gross fungus toenails or something, that'd be about 1 millimeter thick. Or we could be less gross and we could say about the width of a staple. Okay, the thickness of a staple. Maybe that's a little better than a funky toe. So anyways, those are things to have in mind, is how big these units are. Another thing you might want to ask is, how much does the air weigh? Those are very typical questions. So in this case, if I wanted to do the flies, I'm going to say fly is about, I don't know, about that big, about maybe half that wide and about half that tall. So I'm going to say it's roughly 0.5 centimeters by 0.5 centimeters by 1.0 centimeters. So we're assuming rectangular flies. Okay, now some will be bigger than this, some will be smaller than this. And in fact, if you got a collection of them, maybe you take the biggest one you see and the smallest one you see, and you compute their volume, and then you take the geometric mean. So that's a really good estimate too. So you could say the geometric mean. So you could say what maybe the biggest was 0.49 centimeters, and the smallest was 0.20 centimeters cubed. If that was the case, then you take 0.49 cubic centimeters times 0.20 cubic centimeters, and then you take the square root of that, and that would be the geometric mean. So that if you did 3 of them, you'd take a cube root. If you did 5 of them, it'd be a 5th root, so on and so forth. That's what the geometric mean is. So 0.049 times 0.020, and then I take the square root of all that, and I get 0.031. 0.02. Oh, no wonder. I put something in wrong. Ignore that answer. 0.49 times 0.2. Take the square root, and I get 0.313. I'll call that roughly 31 cubic centimeters. So that would be a way you could do it if you had a collection of them. And I'm using a guy by the name of Larry Weinstein, I think is his last name, over at ODU. That's one of the techniques that he uses in his book called Guesstimation 2.0. That's a great book, by the way. I highly recommend it. So let's go on with our number. I'm going to say this is roughly the size of a fly. I know my room is 120 cubic meters. Okay. And I want to divide it by the width of this, or the volume of this fly, which is 1/2 times 1/2, which would be 0.25, times 1, which is 0.25. So this is 0.25 cubic centimeters. Well, I need the same units, or it doesn't come out to be flies, because that's cubic centimeters per fly. So what I'm going to do is I'm going to say, well, 100 centimeters is equal to 1 meter, and then I'm going to cube that. So basically, I got to take 120 divided by 0.25, and then divide it again by a million. So let's see what we get. 120 divided by, I'm going to do parenthesis, 0.25 divided by parenthesis 100 times 100 times 100. There's that parenthesis is closed. So this should give me the right answer. And I get roughly 480 million. So I've seen on TikTok, Instagram, all these things where like people go and buy a bunch of boxes of Fruit Loops and then fill somebody's shower up with it. And then they get about halfway done and realize they don't have nearly enough Fruit Loops. Well, you can do better than that because you've had a physics class, right? So that's a quick way of estimating. I'm going to need 480 million flies to fill up a room. That's basically I said that was 24 feet by 15 feet by 9 feet tall. So that's another estimate that's good to make, and you should be able to make these again at any time. For instance, another one I've seen in a more or less a conceptual level physics is you realize that a cubic meter of the Earth's surface has about 1,200 watts of sun energy hitting it per second. Or so I should say roughly 1,200 joules of energy every second, which is the equivalent of roughly 1200 watts. So you also know, probably, hopefully you've heard that solar panels are only about 10% efficient. So you might say, well, how many square miles of solar panels would we need to be able to power the United States? Well, all you have to do is look up the energy consumption of the US for a given year, and then divide that by basically how much a 1 meter by 1 meter panel can handle, and then you'll have basically the number of 1 meter by 1 meter panels that you'll need, and then you can add up all those areas and get the area of the actual total solar panel. And you'll find it's not that big. People say you'd have to cover out the whole Northwest. No, you would not. You wouldn't. In fact, you wouldn't even have to cover up the whole state of West Virginia. It's even smaller than that. So those are nice calculations you should be able to make, and that's what this book is talking about, and that's why we're going to repeatedly use stuff like that. Your book has some other examples. You might be able to say, okay, how many times will a human's heart beat in a lifetime? That's a very typical one. Or how many times will the moon circle the earth during a man's lifetime, or a woman's lifetime, or a human's lifetime? Okay, all those are different things you could calculate and just estimate. One thing I will give you, in addition to this geometric mean thing, is I will remind you that in fact, the number of seconds per year, 1 year, is actually 365.2, I'm going to say approximately 25 years, days, excuse me. And I know that 1 day is 24 hours. And I know that 1 hour is 3,600 seconds. These are all things you should know off the top of your head. You might not know this one, but you do know that 1 hour is 60 minutes and 1 minute is 60 seconds. So you probably realize if you multiply 60 by 60, you get 3,600, because if you multiply 6 by 6, you get 3/6. And if you then multiply that by 10 times 10, you get 3,600. Well, if you did this math, you would come out with the exact right answer. But it turns out 1 year is also approximately equal to pi times 10 to the 7th seconds. So you're thinking 3.14 times 10 to the 7th. That's a really good estimate. It turns out it's actually 3.15 if you want to carry 2 decimal places. But that's another thing that you can use. That would be, say, a constant that you could put on your equation sheet for your test if you wanted to. Okay. All right, so those are some of the approximations you should make. Now, the last thing I want to cover for chapter 1 really is dimensional analysis. And you could also say it's unit analysis. So unit analysis is a little different because you have to use a specific set of dimension of units. But basically, the unit for length, or the dimension for length in this, is L, mass is M, and time is capital T. Whereas in dimensional analysis, we would use the meter, the kilo, or the gram, and actually, technically, you should probably use a kilogram, and then the second. That's the only difference. So we use a generic thing called capital L for the dimension of length, whereas we'd use meters if we were doing unit analysis. We would use capital M for mass. We'd use kilograms for unit analysis. We'd use capital T for time, and we'd use seconds for unit analysis. So the importance of it is that when you have an equation, part of what you didn't learn in algebra is that equation has x's, y's, z's, and whatnot with various units and various dimensions. And since it's an equation, not only do the numerical values on each side of the equation have to be equal, but the dimensional values have to be equal, and the unit values have to be equal. If the dimensions are true, that are automatically equal, then the units are automatically equal. So you don't have to do both. It's just a matter of that has to be true. So if I told you, for instance, the dimension of energy, actually, let's start a little simpler. if I told you the dimension of force, which I happen to know, is ml over t squared, and I'll tell you it depends on mass and acceleration, which has units of L over T squared, okay, then you can use that to figure out an equation relating M and A to make F. So what we would do is we'd say F dimensions is equal to M dimensions, say, to the P power times A to the, let's say, Q power. So by saying this, I can actually work out an equation that might actually be the right equation. Y'all probably know what equation we're going for, but this will actually give you the right one, and it'll give you the right one exactly right, not even missing a constant. So what I do is I write the dimensions for F is ml over t squared, which is also equal to m to the 1 power, L to the 1 power, and t to the -2 power. And I'd write the unit for mass is just m to the p. And I'd write the unit for acceleration, which is L over t squared. That's raised to the q power. So I've got m to the p, L to the q, and t to the -2q. Okay. Well, you can see automatically p's got to equal 1. L as our Q has got to equal 1. And then if you're right, then those two answers should give us the right thing for T. If they don't, then there's no such equation. Okay. So -2 has to equal -2Q. And we found that Q was 1. So that in fact works. So it turns out the P and the Q must be 1. So we get F is equal to M times A, which is exactly Newton's second law. Now, I could have done exactly the same thing with unit analysis. I could have said kilograms meters per second squared is equal to kilograms to the P times meters per second squared to the Q. And then I'd get kilograms to the 1, meters to the 1, S to the -2. And I get kilograms to the P, meters to the 1, and S to the -2Q. And in fact, I'd get exactly the same results. That's the difference between unit analysis and dimensional analysis. Anybody have any questions on that? Okay. Well, here's another neat thing you might be able to guess. Well, if I tell you the energy E has units of our dimensions of, let's say, mass length squared over t squared, and I tell you that mass is what energy is going to depend on, so that has the dimension of m, and let's say velocity is something else I think the energy will depend on, then I know that velocity is L over t, length over time. So I would like you to work out a equation / formula for E of M and V. In other words, you're going to make E equal to some functions of M times V, or M divided by V, or M plus V, all that sort of stuff. So you can do it just like I did. You're going to put M to the P power and V to the Q power and work out what P and Q are and see what you get. All right, I'm going to get started on mine. Y'all keep working, but if you're stuck on the first step, take a chance to look at this first step. I'm going to say ml squared over t squared is equal to m to the p times L over T to the Q. That's the first step. That should be your second step. Has anybody got a value for P yet?
One.
Yes. Anybody get a value for Q yet?
2.
Yep. Very good. So we actually have two versions of this that works really right. One is exactly correct, and that's E equals mc squared. C is the speed of light, which is a velocity, right? So that's why that works. But we also have another one, which is kinetic energy is equal to 1/2 mv squared. Notice though, you couldn't catch that 1/2 by it. Okay, dimensional analysis will not give you constants that have no units. It can only give you, basically multipliers of things with units. If you thought something was additive, then you got to remember you have to have the same units or the same dimensions in order to add two things. You've heard the expression, this is apples and oranges, or you can't add apples and oranges. Well, that's true, because the unit of an apple is one apple and the unit of an orange is one orange, and apples plus oranges just gives you the number of apples plus the number of oranges, no more than you can add 1x to 2y, right? Because they're not like variables. Same thing here. So if you think a formula might have a plus in it somewhere, then each of the terms in the plus have to have the same units and the same dimensions as well. Any questions on that?
I'm kind of confused on how, so like you're saying basically you couldn't get that formula from dimensional analysis?
Not the 1/2 one, no.
Okay.
You notice it's the same form as the mc squared. It's mass times some velocity squared. So it actually gave us exactly the right one for E equals mc squared, and the Animaniacs even did an episode on this. Okay. So if you like the Animaniacs, you can check that out with Dot and whatnot. Kinetic energy, we get it another way by integration, basically. It was called the oomph by Madame du Châtelet, and Madame du Châtelet was the first person to ever translate Newton's Principia from Latin to one of the Vulgate languages, which in her case, you might guess, was French. She was an impressive woman. At the age of 16, she translated Newton's Principia to French. By the age of 25, she had Voltaire as sort of her boy toy, even though she was married, by the way. That's another issue, but still very impressive character in history. And then she died during childbirth. It's sad, but a brilliant mind. And she is the one that gave us the idea of kinetic energy, and she called it oomph, which I kind of like too.
So it'd be like you have to get a way for volume, or sorry, velocity to go to the speed of light.
Sort of. So basically what it turns out to be, I think your question was like, how do you get to the speed of light? It turns out you're going to have to put in an infinite amount of energy. If that's your question. The E equals mc squared is actually a neat thing that happens to be true with every bit of energy you have. So you remember that Joseph Priestley, I think, experiment where he took wood and he set it on fire, and then he captured all the ash and dust and everything that settled out when the fire was gone, and he weighed all that and found out that that weighed exactly as much as the wood did before he burned. So he said mass was conserved.
Mm-hmm.
Well, if he really did that experiment with and I won't even say this is modern day equipment because we're not that technologically advanced yet. But if we did it with some equipment that could go out to say 16 decimal places, he would find that answer to be wrong. He would find that in fact, the ash weight would be a little bit less than the wood weight. And that ash weight would be exactly the amount of energy that was put out by the fire divided by the square of the speed of light. And that's true for every reaction. So if you actually weighed the fuel that you put in your car, let's say it was brand new, or you just got a brand new gas tank and fuel lines, you cleared all that stuff up, you weighed exactly the amount of gasoline that you put in your car, you drove it till it ran out of gas, which is supposed to be bad on your fuel injector. So don't do that. I do it all the time, by the way. I experiment with my gas meter just to see how far I can go beyond empty. So don't recommend that. It's not good. But anyways, if you do that, then you actually time's all okay. I was just stammering because I looked at the time. I was afraid I got past it. But yeah, if you do that, then you can determine how much energy was created by the gasoline. And you can weigh all the dust and debris that's left in your fuel lines, your fuel tank, your fuel injectors, all that stuff. And what you'd find if you had an infinite number of decimal places, or probably at least 16 or so, you would find that the mass of the fuel residue that's left over is a little bit less than the mass of the gas that you put in. And that amount less would be equal to E over C squared, where E is the amount of energy you got from the gas tank. In other words, how far you went, how much work you did on the car, that sort of thing. Any question on that?
No, that makes sense. Thank you.
Yeah, we'll get to relativity. We do that in here right after chapter 10. We go to chapter 36 and then chapter 11 after that. So you do get relativity in here, just special relativity. Does anybody have any questions on this dimensional analysis or unit analysis, anything like that? All right, here's one more neat dimensional analysis. I'm going to let you do this one. And this is one that we use in engineering. I worked as a structural engineer. I say work as a structural engineer because legally, until you get your official licensure, you're not allowed to say you're an engineer. And actually, none of my degrees are in engineering. I'm just a physicist, and physicists basically have all the science they need to do engineering. They just need some experience in the world. And I basically gave that to myself through building and reading, and became a structural engineer. And in the Outer Banks, I was a structural engineer. And when you do it on the Outer Banks, you have to deal with something called hurricanes. And hurricanes basically put forces on buildings via pressure. So I might tell you, for instance, that the unit of pressure, which is P, is newtons per square meter. Okay, you probably know it as pounds per square inch, and that's certainly fine. In engineering, we use pounds per square feet. That's the normal unit. And for instance, you're supposed to design a typical house to withstand 30 pounds every square foot of the floor. So when you go to design a floor, you have to lay out basically a foundation that has piers and stuff like that. And then you choose whether you use a 2x4, a 2x6, a 2x8, based on how large of a span you got. The numbers you have to use are 30 pounds per square foot. And if you're in a library, it might be as much as 150 pounds per square foot. If it's a deck, I think they were starting to make people do 100 pounds per square foot because we've had so many injuries from decks collapsing during parties. So lately, the housing code has been requiring that. But anyways, that's what pressure is. And that's really what we have to deal with when we're dealing either with designing beams or choosing 2x4s over 2x6s over 2x8s over 2x10s or 2x12s, or MVLs or LVLs or any of those kind of things. So we have to do that. But in the Outer Banks, we have to do it as a result of wind as well. So not just vertical loads, but lateral loads due to wind. So we can work this out. I know that the Newton is equal to 1 kilogram meter per second squared. So you can see this is also called the Pascal. That's another unit that we use, but it's actually Newton per meter squared is a Pascal. So what I want to say is I want an equation for for pressure, and I suspect it's going to be related to the density of water, or excuse me, the density of air, and the velocity of the air. So I'm going to say P to the, I probably shouldn't use P here since I'm using P on the other thing. I'll say Q and L. So velocity to the L power, density to the Q power is equal to some P. And believe it or not, you actually get a pretty good result here as well. So what I know is velocity has units of meters per second. And I know that density has units of kilograms per cubic meter. Now, I could do this with dimensions, and I really prefer dimensions, to be honest with you, but I just wanted to show you one with units just in case. So now what I'm going to do is I'm going to write one. Actually, I don't even need the one. I'm going to write kilogram meter per second squared per meter squared. That's what pressure is. That's newtons per square meter. See, is equal to kilograms per meters cubed to the Q power times meters per second to the L power. Let's see if you guys can work out what Q and L are. I'm going to do it alongside of you, but I want you guys to get started. And then if you just can't get started, wait for my first step. Okay, so hopefully y'all got that Q was 1, L was 2, and then you double check to make sure that L minus 3Q was in fact equal to -1. Did everybody get that? Or anybody have any questions about that?
I am kind of lost.
Okay, so all we did is we basically said, I want an equation for pressure, and I suspect pressure is going to be related to the density of air and the velocity of the air. In other words, the wind speed, right? So I just conjectured that it'll be a multiplicative formula. So I'm multiplying P to some value times Q to V to some value. In other words, P raised to the Q power and V raised to the L power. Now I just took my units and put them in. What I know is the unit of pressure is newtons per square meter, and I know the Newton is a kilogram meter per second squared. So that's my Newton, and the meter squared on the bottom is this. And then I said, well, the units for density are kilograms per cubic meter. So I put them in parentheses and raise it to the Q power. And then the units for velocity is meters per second. So I put that in parentheses and raise it to the L power. Now I'm just doing algebra. I'm treating this like X, Y, Z squared, Q squared, and doing the arithmetic and algebra stuff. I found that the kilograms, meters over meter squared, second squared ends up becoming kilograms to the 1 power. Meters to the 1 divided by meters to the 2 is meters to the -1. And second squared in the bottom is seconds to the -2 power. Then I just broke this up into kilograms to the Q power and meters to the -3 q power, because it's cubed already. And then a power to a power, you multiply. So that's where I got the -3q. And then also I had m to the L power. So when you multiply like bases, you add the exponents. So it's L plus -3q, which is why I got L minus 3q. And then this S is just to the -L power. All I had to do at that point is figure out, well, kilogram is supposed to be 1. So that suggests Q is 1. Meters is supposed to be, or let's not do that. That's more complicated. Seconds is supposed to be -2. So that would suggest L should be 2. And then I got to make sure the other one's true, or else my equation just can't be made with those quantities. So what I did is I took L equal 2 and Q equal 1. So 2 minus 3 times 1 is 2 minus 3. That's -1, which is what that is. So that's why it checked. So ultimately what I found out is that pressure is density times velocity squared. And that is actually Bernoulli's equation. Bernoulli's equation just gives like that. And that is exactly the formula I used. They have the ASCE 798 manual that tells you how to do wind velocity calculations, or excuse me, wind pressure analysis. And there's factors you put in front of this for various things, like if there's a hill nearby, escarpment's what they call it. If the building goes over a certain height, you have to do some other things. But other than that, you're just basically using 1/2 rho v squared to find the pressure on a building. And then local code will tell you what the max pressure is. So like if I go to build a house out in Hatteras, or I design a house out in Hatteras, or even Ocracoke, then I'm required to use a wind velocity of 150 miles per hour. It's either 150 or 140, whereas the rest of Dare is like 120 miles per hour and Currituck's 120 miles per hour. So then you just build the house, making sure that it can sustain those lateral pressures with drag struts and stuff like that. Sometimes you have to put, specify that you have to have a nail every 3 inches around the border, and then every 10 inches along the insides. Sometimes you even have to put plywood on both sides of the wood wall just to account for the stresses. But does everybody have some sense of what we're doing here with dimensional analysis and this time unit analysis? I think you can see dimensional analysis is a little cleaner than unit analysis. It's real easy to accidentally get that K and G separated. Time's technically up, so everybody's free to go if they like, but I'm going to wait here for the last person to ask me questions. You should learn the prefixes for the SI system in the front cover of your textbook. I used the great monarch King Henry died by drinking chocolate milk. And then I go to 3rd grade mentality when I do the mu and the n. So, or excuse me, the U and the P. So you guys are gonna have to figure out that for yourself if you want a mnemonic. I don't want to be the gross guy that tells something dirty for a mnemonic.
Professor?
Yes, ma'am.
I hate to say it, I somehow can't find the course ID to log into Mastering to do the homework. Where is that?
You're not supposed to use it. My course is integrated. So what you have to do is go to my Canvas page and then click on Chapter 1 homework.
I got you. Okay, I'll try it out. Thank you.
Yeah, if you try to go the other way and you succeed, which you can by hacking, then I will never get to see your grades.
Okay.
That's your problem. Okay.
All right.
Good luck, Julie. Anybody else have any questions?
I have a question for the lab report.
Okay, go for it.
I just wanted to know, with when we're doing averages, do we also include uncertainty?
You mean like are you talk about like doing a weighted average or something like that?
No, because when you were explaining it, it was like X bar plus.
Gotcha. Yeah, I know what
do
you're
we
saying. I
include
realize that. No, you don't have to do that. The average, you're just going to take the basically your measurement plus your next measurement plus your next measurement. I'll add them all up and divide by the number, and that'll be fine.
Okay, thank you. I just didn't know if I had to include the uncertainty yet.
No, where the uncertainty would actually come in is if you took the mean and standard deviation and then calculated the standard error, you would use that to round it to the proper number of digits. What you're going to do instead, since we're not doing that in this lab yet, is you're just going to add them all up and use significant digit rules to round it to the appropriate place.
All right, thank you.
No problem. Ailey, Emilio, Carlin, Damien, Amy, Moel, do you have any questions?
I just wanted to backtrack on my lab assignment. So you know how you go on Canvas and it's just like right there. We don't have to go through that, or
No, you can go right to the My Lab and Mastering on the left-hand side. I'm not sure as a student where that drops you off at, but then you can look for assignments, and that'll be where the homework assignments are. Or in each module for each week, I'll have a chapter conceptual homework plus a chapter link for the problems, maybe two, because some chapters have two problem sets. So you can click on one of those and that'll take you straight to the assignment, or you can click on My Lab and Mastering on the left-hand side, and that'll take you to the generic front page of My Lab and Mastering.
all right, thank you. I was just trying to figure it out.
Yeah, just make sure you go through Canvas, because if you try to do it any other way, it's going to just balk and mess up. Anyone
All
else?
right, thank you.
You're welcome.
I kind of have a strange case with my lab. The way we took data in it, I think I had to do this 2 days ago, but the way we took it, I don't actually have the amount of data that I would need to calculate their pi values. So what should I do with that? Because I don't know if I can contact them now.
Yeah, you should try to contact them. Do you remember their names at all?
I do not. I know one was Delaney, but I don't know.
Okay, well, actually, if you contact Delaney, she might have gotten the information. You don't have to have their values to calculate pi. What you're wanting is didn't the table just say your 5 values of pi and their 5 values of pi?
It had my 5 values of pi, but like the way we did it, we all did a couple of them. So I didn't actually have 5.
Okay, yeah. So each of you were supposed to have 5 objects. If you only had 3, then you take your 3. If Delaney had 5, you get her 5 values of pi, and the other lab students, if they have it, then they get that value. But the good news is we'll have class on Tuesday, and you should just announce that at the beginning, and your lab partners will let you know what they had for their pi values, and then you can either contact them after class, let them send you their email or phone number or something, and you can get that and just put it in the lab report before 1:30.
Okay, so we're gonna be working in the same lab tomorrow or on Tuesday?
No, but you're all in the same class. What I've determined is everybody in this class is in my lab.
Okay.
So I don't think there's anybody in the lab with you that wasn't from our class.
All right, cool.
All right. See you, Silas.
Actually,
Anybody else? Yeah, go ahead.
Is there a way, I just want to see if we could make the camera clear. Have you tried like using your phone as a second screen?
Yeah, the phone actually turned out to be worse just because it's got a smaller aperture. The resolution's worse. The good news is, like I said, when it goes up video wise, it's much better on YouTube because the bandwidth isn't a problem in going from the camera to the computer. The bandwidth's the problem in going from the computer and the camera to you.
Okay.
So the videos that I put on YouTube will be a lot clearer. I apologize for that. I wish our internet was faster out here in the boonies. Speaking of which, did y'all hear they've extended the out of class online portion until the 30th of January, 31st?
Yeah, I did hear that. Yeah.
Okay. Just I meant to mention that in class, but I forgot till now. Anybody else? All right, well, I got to go because it's time for my next class. Feel free to email me or if you have any other questions. Have a good day.
Yep, thank you. Have a good one.
Thank you. Bye-bye.